Uh, so yeah, welcome everyone. So to this CFD series. So this will be the last video or tutorial in this series of CFD. So in this we'll cover the turbulence schemes and then so turbulence modeling and then in some parts of advanced CFD. So let's directly get straight into it. So before jumping into turbulence modeling, I'll first cover up something called the Riemann problem. Okay, it's too big. So I'll just give it. Yeah. Okay. So yeah. So this is the Riemann problem. So what is this? It's a very classical theoretical problem. So imagine there's a wall here. I call this the left side, and I call this the right side. Right. Here I have the parameters of, like, suppose pressure is 10, 10. I don't know. Let's take it 10 atm. Here rho is 10 kg per meter cube, and here I take P is equals to 1 atm and rho is equals to 2 kg per meter cube. Okay, if I remove this wall or this divider, right? So if I remove this wall or divider, remove, what will be the state of um, this region, right? So what will happen? How will the flow occur is what I am concerned. So this, so what you do is, if you know what happens in this case, you can compute flux, right? Compute flux easily. So this is why you need solvers called Riemann solvers. Riemann solvers, right? So you will find cases where you have constraints. So it doesn't have to be a physical wall, but mostly let's assume it's to be a physical wall or some barrier. And if that constraint or barrier is removed suddenly, what would be the dynamics or fluid behavior when the wall is removed, right? What is the interaction of the fluid is what we want to know. So to solve that, you have Riemann solvers. So the most famous out of all this is your row scheme, ROESCHEME, so the row scheme method. So this is an approximate Riemann solver, right? So let's say what does this does is it replaces uh, complex non-linear equations equations into I mean, it replaces them with a linearized version, right? Linearized version. So this makes it easier for the solver to solve. So this is fast. So this is fast because you are approximating and converting into linear equations. So this is fast, but there's a disadvantage that it can creates negative density and pressure and pressure sometimes, which is not possible. So that's just a flaw. Of course, negative density is something that you cannot have. So physically, it's not something that you need. So that is one disadvantage of this method. So then you have like you have different methods. Like another one is AUSM. Now going deep because it's not much needed. So this is advection uh, upstream. Advection upstream. If I remember, S was, I guess, splitting. It's splitting, and M is the method. So advection upstream splitting method. So this separates here. It this You have a separation between mass transport, okay, and your pressure. So what it does is it separates these two and solves independently instead of treating them together. Okay, that's all this does. And then you have a famous, relatively famous one, that is your HLLC, right? So this is used for capturing shocks and discontinuities. Shocks and discontinuities. You don't need to know how it works, so I'll just skip on that, right? So this was just a general overview of the Riemann problem, right? So Riemann problem, just for a gist again, you have a left side, you have a right side. Let's say you have P, you have rho, and you have P, and you have rho, right? So um, yeah, if you have a wall that separates, then if you remove this wall, what will be the conditions is what we need to know. So that is what the Riemann problem is, and you have multiple solvers like row scheme, the most used one. You have AUSM, and you have HLCC. You even have flux splitting, so you just divide uh, one flux into positive moving and negative moving flux. So yeah, just that is this is just to have a gist on. There's nothing to know deep. Now something that we need to know in detail is turbulence models, right? So the most important, I would say one of the most important in CFD, that is turbulence modeling. So what is turbulence? Everyone knows it's when your fluids start intermixing, and then there is so there's a change in behavior of fluid, right? So that is what is turbulence. So you define turbulence using Reynolds number. So you have your Re is equals to rho Vd by nu, right? So with this value, you can find the value. I mean, using this value, you can say if it is either a laminar flow or um, a turbulence flow, right? So, so usually, if I can just say that Re greater than 4000 is turbulent flow, okay? Turbulent flow, right? So now this is something we need to model. So how do we do it in CFD? So here, since this constant mixing, so what happens is velocity doesn't remain the same, right? So what are we going to do? So we split the velocity, just simple. Split velocity into two parts. That is your u is equals to u and a dash on top plus u dash. What does this mean? So this is your mean velocity, and this is your fluctuating velocity, right? So this is the velocity that changes based on the mixing and the turbulence flow, and mean velocity is something that remains on an average the same, right? So you split velocities. Now you know how to solve these, the mean velocity ones. Now fluctuating velocities is how you try to encounter. So this decomposition, that is splitting, is what we called Reynolds Reynolds decomposition, right? So now, how do you solve this? Now these are all complex equations, right? So you cannot directly substitute decomposing it into Navier-Stokes and solve, because I mean, you can, but it's going to be heavily, um, um, what do you say, complicated in computation. So what you do is you substitute decomposition position in Navier-Stokes, Navier-Stokes, and average it. Then average it out, average the equations, okay? So what do I mean by substitute decomposition? So in Navier-Stokes equation you have velocity terms, right? So you have, if I'm not wrong, the del rho v. So this v term you have to replace it with u is equals to u dash plus u mean, right? So when you do this, you get an equation, and then you average out equations, right? So why do we need to average it out? This makes the flow equations easy to solve. So flow equations are now easier to solve, are easier to solve, okay? So now what is this called? This whole process, or the equation that we get through this, is what we call RANS. And what is RANS? Reynolds average Reynolds averaged Navier-Stokes Navier-Stokes equation, right? So you substitute the Reynolds decomposition velocity equations into the Navier-Stokes, and then you average it out. That is your Reynolds average Navier-Stokes equation, right? So this is your RANS model. Now, when you do the averaging or the RANS part, you encounter Reynolds stresses. Okay, so this problem, what we call it, the closure problem, the closure problem. So when you are decomposing it and putting it into the the Navier-Stokes equation, you get extra terms, right? Because again, it was, if you remember, it was grad u this, right? So, and there's again multiple terms with velocity. So when you put the decomposition terms, right, you get extra terms like u dash v dash bar, and then rho u dash w dash. So each configuration, right? W dash. So these kind of stuffs appear. So what we call them is Reynolds stresses. Reynolds stresses, right? So this is what. So the momentum transport is caused by turbulence. Caused by turbulence. I'll just explain you what this means. So these Reynolds stresses are technically the reason. It's a causality, or it's the cause of turbulence. So this Reynolds stresses is what we are supposed to find and resolve, right? So this is like, you can say, momentum carriers. So this extra momentum that you get is what causes turbulence. So these Reynolds stresses, I'll just explain it again. So when you decompose and average it, you get these extra terms. Because of the splitting, that is your u is equals to u dash plus u mean. So that's why you'll be getting so these are not the only ones. You'll find more terms. So when these terms appear, these are the Reynolds stresses. So these are responsible for the momentum transfer that is caused by turbulence. Okay, hopefully this was understood. So I can write this as um, Reynolds stress tensor. Wait, before I touch upon this, so yeah, I told this is a closure problem, right? So why is it called the closure problem? So original equation that you had, so once you had split it and then you had averaged it, right? So that was RANS that you had got, right? So now the problem is that now once you try solving for these also, RANS ends up has more variables than uh, than the original one, right? So the original one before averaging had lesser terms than the ones that you had done after averaging. So this is the closure problem. So yeah, so we'll see ahead what happens. So you have Reynolds stress tensor. This is just a way to define your Reynolds stresses. So you take tau of R, that is your stress tensor. You have, it's just simple, you have u dash, just go ahead with the configuration, u dash v dash, u dash w dash, then just keep going, u dash uh, sorry v dash, u dash, v dash v dash, v dash w dash, and here you have w dash u dash, w dash v dash, and w dash w dash. Okay, now this is your Reynolds stress tensor. So this is what causes the turbulence. So I mean momentum transfer. So turbulence causes, or sorry, I can say transports momentum, right? Now this is when a new concept comes in. So how do you resolve all this? Well, what Eddy came up with is this concept called eddy viscosity. Eddy viscosity, right? Concept. So you know the normal viscosity that is new, right? So The normal nu causes a you can say uh, it causes momentum, okay, or change in momentum. So what we as Eddie did is that he assumed that there's some other bigger viscosity that you call it as nu t, and this is called your turbulent viscosity, right? So it's either called turbulent viscosity or eddy viscosity. Okay. So here, yeah. So what Eddie did is he assumed that this is what causes this momentum, this turbulent momentum transfer, right? So he imagined that turbulence is caused due to this, or this momentum transfer is due to this turbulent viscosity. And so if you want to resolve any turbulent flow, if you find this turbulent viscosity, you can resolve rest of the stresses and get an idea of the turbulent flow. So like you take any model in turbulence, that is your k omega, k epsilon. So all of them have uh, they have to find new t first. That is how everything then later gets resolved, right? So yeah, that is the eddy viscosity concept. So just in a gist, so normally you have force, your viscous force, right? That's equals to your this, and I'm not wrong, dv by dA, right? Sorry, dv by dH into A, right? So uh, this viscosity is causing a force that causes the momentum. So here what Eddy realized, or he just assumed, is that there's something called turbulent viscosity which causes a turbulent force which causes the momentum that causes turbulence, right? So and for any flow, any model of turbulence, that is k omega or k SST or k epsilon, you have to find nu t, that is your eddy viscosity first. So hopefully that is understood. So let's go ahead. Now we learn about turbulence scales. So uh, now why do we need turbulence scales, right? I'll just explain what turbulence scales is first, and then I'll continue. So yeah, so let's start with turbulence scales. Turbulence scales, right? So turbulence is generally not uh, one vertex, right? It's like a hierarchy. So turbulence isn't one vertex. It's a hierarchy. So it's like in a layer. And hope you know what's a vertex. So curling of fluid is your vertex. So if you have this fluid going like this, it's a vertex. So that is your vortex, and then so yeah, vorticity, you can just say vorticity is just cross times of your velocity, right? So del cross v is your this thing, and then if you integrate vorticity with related to time, or if that is your del cross v with respect to time, you get circulation, right? Circulation. So if I calculate vorticity over a whole loop, or line integral of that is over time, sorry, over this line is your circulation, right? And your vorticity is your curl of velocity, that is your grad into cross v. So yeah, so turbulence is not one vertex, it's like a hierarchy of vertex, right? So this hierarchy is resolved like this. So you have large eddy, right? So these are energy carriers. So it starts from this, they carry the energy, then large eddy resolves to medium eddy, then goes to small eddy, and then goes to tiny eddy. So you go to tiny eddy, and then this, okay, I'll just leave it here, and then I'll go to the next scale. So these dissipate energy, so they give out energy, right? So the large eddies carry energy, and the tiny eddies dissipate energy, right? So just go to this hierarchy, right? So by eddy here, you can just think it as viscous vortex, right? So the larger ones carry energy, and then as as it becomes small, that is you're giving out energy, right? So there's one more tiny scale, or we call it the Kolmogor series, sorry, scales, Kolmogor scales, right? So these are the tiniest scales of turbulence. Okay, so here viscosity dominates, right? And energy finally becomes heat. Energy becomes heat. So it's the smallest one, so it dissipates energy, and it's dissipated in the form of heat, right? So this is all you have to know. Now we'll just jump into wall treatment. So wall treatment. So in wall treatment, you have, again, this was covered in mesh. So you have boundary layer. So boundary layer regions, I'll just tell these. So you have the wall, then you have a viscous sublayer, then you have buffer layer, buffer layer, you have a layer, and you have an outer layer, right? So in the viscous part, your viscous sublayer, your y plus is around 1. Your buffer layer, your y plus, you can say, is from you know 5 to 30. Okay, y plus is 5 to 30. Your lag layer, your y is 30 to 300. Y plus, I mean, not y. And your buffer layer, buffer layer I had covered. Outer layer is just the outer layer, so I don't consider this fine. So yeah, so what does this mean? Y plus, again, I had mentioned, it's the distance from the wall to the center of the boundary, the inflation layer, uh, in turbulent terms. So you have your turbulent terms, that is rho v L by nu is dynamic viscosity. So instead of L, you put rho v y divided by nu, where y being the distance from the surface, the geometrical surface or the boundary to the center of the inflation layer that you are considering. So that gives you your y plus, right? So yeah, that is something just want to discuss. So these are the different sublayers that we divided into, and they have uses. So we not cover that in this. Just need to know for now, right? So y plus, again, is a very important phenomenon or parameter that we had talked before. So now let's go into the main one. So turbulent models, right? So turbulent models, I'll just go in sequence. So you have DNS. So DNS is direct numerical solution. You have, then it goes, you have LES, large eddy simulation. Then you have DES, detached, that is detached eddy simulation. Then now you get into RANs. So RANs starts with Spallart Almaras. Then you have your K epsilon. Now K epsilon has your standard RNG and realizable, right? Uh, then you go on to K omega. You have standard and SST, standard and SST, and at last you have RSM, that is Reynolds stress model, right? So we'll discuss each of them in detail now. So yeah, before I move on, I'll just discuss the tree again. So you have DNS, that is direct numerical solution. Then you go into LES, that is large eddy simulation, and DES, that is detached eddy simulation. So these are just independent of, all three are independent of each other. Then okay, DES comes under LES, my bad. So DES comes under LES. Yeah, right. So you have DNS, then LES, and DES comes under LES. DES is detached eddy simulation. Then you got RANS. RANS is again, which we just discovered, uh, checked. That is Reynolds average Navier-Stokes equations. So to solve that, you have four models. That is Spallart Almaras, right? Then you have K epsilon. You have standard, RNG, and realizable. And you have K omega. You have again standard and SST. RSM. You have Reynolds stress model. Now we'll look on to each of them in detail, right? So number one, first we'll complete RANs, right? So under RANs, our first one was Spallart. This increase thickness. So Spallart Almaras. Okay, Spallart Almaras. So what does this do? So instead of solving for K, omega, and epsilon, okay, these are again turbulent terms. I'll tell you what each of them mean. They solve for single modified viscosity equation, right? So it solves a single modified viscosity equation, right? So instead of solving for these three terms, it solves one single modified viscosity equation. So because of this, it's fast and less memory is taken, fast and low memory, low memory, right? Uh, yeah. So this is not ideal. Sorry, not ideal for you can say high swirling, because you need a lot of captures in that highly swirling swirling flows. That means where vorticity is high, circulation is high, you cannot use this. Or you can, I mean you can, but it'll be inaccurate, because the terms K, omega, and epsilon are important to capture all those details. So now getting on, the second one is your K epsilon, right? This is your standard K epsilon that I'm talking about first. So K epsilon, so what is K? K is your turbulent kinetic energy, okay? And this is equals to half times your u dash square plus v dash square plus w dash square, right? So what is this dash? This was the turbulent after splitting, so u is equals to u mean plus this, right? These are the turbulent velocities, right? So the half times of the sum of all those, uh, sum of the squares of all those will give you your turbulent kinetic energy. And now let's take epsilon. So epsilon is rate of turbulence dissipation. So what does this mean? So now we had checked the hierarchy, right? So you had large eddy, you had medium eddy, tiny, small eddy, and tiny eddy, and then you have the Corollo, the what do you call the Kolmogger, the Kolmogger scales. So Kolmogger scales being the shortest of, I mean, the tiniest of them. So yeah, so what is epsilon to do with that? So as I told, the tiniest scale, so either sorry, tiny eddy or Kolmogger is, I mean, they dissipate energy, right? They dissipate energy. So that the rate at which this energy is dissipated is what is epsilon. So yeah, moving. So yeah, once you have calculated k and epsilon, so now what you do is you calculate nu t. So this is your eddy viscosity, right? So you calculate eddy viscosity. So this is extremely fast. extremely fast. It's robust and fast. So robust means it's very accurate and fast, but it's very poor at separations, separations and boundary layers, right? Separations and wall. So the predictions it makes at walls and separations are very poor. So that's why you normally don't use standard K epsilon if it's if your fluid, if you know the fluid is gonna behave very different at the boundaries, then you don't use the K epsilon the K epsilon model, because then you will be getting the wrong details, right? So I don't know. You can just use this for like pipe flow, or HVAC. HVAC is the cooling systems and heat exchanges. So here, heat exchange, HVAC, that is the cooling, and pipe flow, the boundary or the walls don't matter, and there's not much flow separation or boundary layer separations there. So you can use the K epsilon model there. Now, under K epsilon, you have the standard which we looked upon now. Then um, you have K epsilon RNG. So RNG is renormalized group, renormalized group, right? So this solves for K and epsilon, but with improved equations. So you converge faster. I mean, you get um, results faster, and this is mostly used for rotating flow, rotating or curved flow, right? Well, that's all you need to know about this. So at separation, this does kind of moderate, but again, you don't use this for separations. Um, then the next one you have is realizable K epsilon, realizable K epsilon. So this is again modified equations. So these are just built upon the standard K epsilon, right? So it's just not much changes, just for faster and more accurate results. So modified formulations, formulations. So, and this is all related, but here it is the modified formulations are to make sure that the Reynolds stresses, Reynolds Reynolds stresses are accurately resolved, accurately resolved, right? Now coming back to the next one, it's your K omega, and we'll go on to standard. So one of the most important models in your turbulent flow. So here again, now it solves K and omega. So K, I told you what it is: kinetic energy, turbulent kinetic energy. Now omega is specific dissipation rate, specific dissipation dissipation rate, right? So this is another term closely related to epsilon, but there are differences between epsilon and omega. So the K omega solves for K and omega. So this is related to again your scales. So you go with each hierarchical. So for each stage you calculate the dissipation rate, right? So it's very specific. So so here again, after calculating this two, you calculate nu t, that is your eddy viscosity, viscosity, right? So the matter with this is that it has excellent near wall near wall predictions. So it resolves the wall regions or the boundary layers or the boundary separation layers very accurately. So it's sensitive to free stream conditions. So it gives weird results in free stream condition. But now what do I mean by that? So if I have flow going like this, right? Right? Suppose this is my flow. So this is my near wall. So this is my boundary, and this I would call as my free stream. So in free stream, that is apart. I mean that is away from the walls, and kind of less turbulent, what happens is that this model, that's the K omega SST standard, gives weird values, right? So now if you can see, there's like an analogy. So it's like your K epsilon does good at free stream that is away from walls. Your K omega does good at walls, right? So you know where we are going with this. Um, so this was K omega standard. Now we have a combination of two, that is your K omega SST. So you have K omega SST, right? That is, so your SST is a shear stress transport. So SST means shear stress transport. So what does K omega SST do? Well, very simple. So when it's near, for near wall, it uses K omega, K omega near wall, and K epsilon away from wall. That's when it's more like a free stream condition away from wall. So this is a brilliant idea, right? So that was you, when you merge the good things and the bad things of one of both the models, you get an extremely better model. So that's the K omega SST, right? So K omega was doing bad near walls. Sorry, K epsilon was doing bad near walls. So um, you put K omega into this model where it does near good near walls, and for away from walls, you have K epsilon handling it, right? So this handles flow separation very well. Handles handles flow separation very well, very well, right? So yeah, this is technically your K omega SST, one of the most used turbulent model, right? So here you usually require, I mean, you can have y plus u around 1. You can even have greater because, uh, I mean, you can even have 32 y plus to 300. You again, you always generally go for lower one because you have an SST omega model on here. So just if I just go back for K omega, you need y plus from 30 to 300. For SST, since it's near walls, you need more fine mesh refinement near the wall. So you can tell it as y plus less than or equals around 1. So yeah, this is uh, one. These are the important models. So now you have another, that is your RSM. This is Reynolds stress model. Stress model. So what does this do? It's just simple. So it just, instead of two equations, it solves six equations plus one dissipation equation. So instead of solving for either k or omega and then finding new t, what it does is it solves for the stress. So there's six stress equations. So it directly resolves the Reynolds stresses. So six stress equations plus one dissipation dissipation equation, right? So it captures swirl. So you can capture swirls, but it is harder to converge, right? Because here what you're doing is you're ignoring the viscosities. You're just directly solving the stresses and the dissipation. So you're playing around with energy over here. So that's why you have the other models above. But this is also a model that is still used in CFD. So yeah. Now moving on. So now we have completed RANs, right? So we have completed the RANs part of it. So we had your K omega, K epsilon, K omega, then K omega SST, and then you have your R Reynolds stress model, so RSM, right? So we are done with RANs. Now we'll be jumping into the upper ones. So you have LES. So that was number 8 if I'm not wrong. So okay, sorry. LES. So large eddy simulation. So now if you remember the hierarchy that we followed, right, or the turbulence scales, You remember that it was large eddy, then medium eddy, small, and then tiny eddy, and then you have your Kolmogor series, right? Or scales. So here what you do is you resolve the model, or the solver resolves large eddies, large eddies directly, and it only models tiny eddies, right? So it solves, I mean, it resolves large eddies directly, in the sense that it solves the equations related to the large eddies and then just models tiny eddies to just check the behavior. And this is accurate. So this is accurate, and it captures vortex shading, right? So it's a very useful, and LES is still used very much to this extent. So you have an other, okay, so vortex shading, this directly you can tell it as it's good for turbulent mixing, right? So hope you understood LES. Now jumping on to DES, or detached eddy sim, right? So in detached eddy simulation, it's an hybrid. So what you do is near walls you use RANs, right? And away you use LES. So this is so again, your LES is not that good at near wall resolving, and that is one of the disadvantages of LES. That's why it's good for vortex shading. So your vortex shading usually happens within the middle, or the free flow stream, right? Um, and the mixing usually happens there. So LES is a bit weak on the near wall resolving, and that's why you have DES. So detached eddy simulation is where you use RANS, or the Reynolds average Navier-Stokes equation, um, near walls, and so that includes your k omega SST, k epsilon, and your RSM, and away you use your large eddy simulation, right? Again, a very much um, used model. So usually if you see aircraft wakes, so aircraft wakes are usually determined through this, right? So, or model through this, I mean. So now the 10th and last one, DNS. It's like the dad of all models, the direct numeric numerical solution. So what is this? What is DNS? Well, what did we first see was that we put in the Navier-Stokes, right? I mean, we had Navier-Stokes equation, and we had also we had split velocities into u dash plus u mean, right? And where this was the I mean, this was the turbulent velocity, right? So what, and this was the mean one, mean velocity, mean velocity. So this was Reynolds decomposition, right? We had split velocities, and then we put this into the Navier-Stokes and averaged it to form RANs, correct? Now, what DNS does is it completely removes the averaging part. So we did talk that if you put directly into this, it becomes very complicated, right? That's why you average it out and form RANs, that is your averaged equations, which are easier to solve. But what DNS does is it directly solves the Navier-Stokes equation with the Reynolds decomposition put into it. So solves all the equations, right, that are related to the Navier-Stokes after putting all the decompositions. So it includes all the scales, all scales, that is from large to Kolmogorov scales, right? That is from the largest to the tiniest, and and there's no doubt it's the most accurate. But what is, I mean, why is it most accurate? Because you're literally solving the equation as it is. You're not averaging it, so there's no approximations. You're directly solving, and you're resolving for all scales. So in LES, you are only resolving large scale, and you are just modeling the tiny ones, and the medium and tiny, and the Kolmogorov scales. So here you are resolving all scales, and you're solving equations related to all of them. So this is the most accurate turbulent model, but again, what is the trade-off? It is highly costly, and heavy computation. Heavy computation. Of course, you are solving the original equations, computation, and hence it takes more time, right? So this was the turbulent models that we saw. So again, if we just recollect, right? So you have DNS, a direct numerical solution, the DAD. Then you have LES, large eddy simulation. So this only resolves the large eddies and then models the tinier ones, and it resolves the equation and solves the equation related to them. Then you have DES. So this comes under LES. So DES uses LES, that is your large eddy simulation, for uh, region where it is away from the wall, and it uses RANS equation where it is near the wall, right? So then you have RANS, that is Reynolds average Navier-Stokes, and now in this you have K epsilon, you have K omega, and under this you have K omega SST, right? And then you have Spallart Almaras. So Spallart Almaras is where you have one modified equation. It's Marasf, yeah, Spallart Almaras. And then you have your RSM, your Reynolds stress model, where you're solving for the stresses. That is 6 stress equations plus 1 dissipation equation. Spallart Almaras, you have one modified equation. So instead of calculating K or omega, it doesn't do any of that. It just solves one modified equation for a turbulent term and then finds viscosity, the turbulent viscosity. Here you have K omega, um, that is omega is a specific dissipation rate, and K is your turbulent kinetic energy. Your epsilon is now then you, I mean, so K omega is used for near walls. It's very highly efficient. So you have your y plus less than or equals to 1, and K omega SST is where you use K epsilon for away from walls and K omega for near walls. So K epsilon is that model. So where you have epsilon, that is your turbulent dissipation rate. So the rate of dissipation of turbulent energy across the scales, right, that we saw. So this is used more when it is away from the walls, so like a free flow stream. So we have seen all this, and hopefully now you know the models. So this is the end of turbulence, right? So we have covered everything in under turbulence and turbulent models, right? So this is more like an end. Now, if there are like like small advanced CFD topics, I'll just go through in short. We don't need much. So one is dynamic meshing, right? So you have dynamic meshing. So in dynamic meshing, what does it mean? It technically means, so if your geometry is moving, right? Geometry is moving, your mesh also moves, or it has to regenerate. So that is what is um, yeah, dynamic meshing, right? Not going anything in detail. So for this, I mean, because when your object is moving, suppose you have um, uh, I know propeller, right? And it's rotating. So the mesh and this, okay, and this, it's connected to another axle, right? So when it's rotating, or suppose there's an object over here and it's sliding with that object every time, so the mesh keeps getting distorted, right? So there are methods that you can use for dynamic meshing. One is smoothing, right? So you move the nodes or you move the mesh elements smoothly. Then you have remeshing. So you mesh it every time it starts moving, or if it is coming in contact with another object, like sliding. And then you have layering. So layering is where you put a new layer of mesh, just regenerates or comes. You just put it on top of the old mesh, right? So that is everything about dynamic meshing, right? uh, Apart from this, you have an important topic, that's FSI, FSI, or that is fluid structure interaction, right? So just imagine if your air is pushing air is pushing fins, the fins, right? Fins. Okay, I'll just explain it diagrammatically. So in a rocket, oh my God, it's looking like some obvious rocket, but yeah. So imagine this is the rocket and the fuels. So you have fins, right? Suppose let's assume you have trapezoidal fins, right? You have trapezoidal fins. So when air hits it, it's possible that it gets deformed, right? So if because the velocity of air is like, I don't know, like let's assume this rocket is going on at 1 Mach, right? That is at the speed of sound. So velocity is huge. At it's like around 300 meter per second, right? So when it hits the fins, of course your fins will get slightly distorted. So that you calculate using the deformation, you calculate using FEM, right? How much it gets distorted, as we have discussed before in the first session. And then so once it's distorted, you have to mesh it again, and your fluid interaction, I mean your fluid behavior changes now, right? So when it was flat, like when the fin was like this, fluid interaction is different. When it is a bit distorted, now your fluid interaction changes. There might be even introduction of turbulence with just change in geometry, right? So this is your FSI, that is your fluid structure um, interaction. So it's like when the geometries keep getting changed, your CFD also changes. So it's just a aggregate or joint, uh, it's like just a joint of CFD and FEM. So and each of them are related to each other. So you have one way and two way FSI. So where like when there's some distorted FEM, I mean distorted body, then the CFD changes. It is CFD. Huh. And two way is when it's both the sides. So because of the air, the the fins get distorted, and now on the distortion you have to calculate a new, you have to simulate the new behavior of fluid. So it just keeps going back and forth. So that is your FSI, or fluid structure interaction. So these are all advanced CFD, because you have to calculate then at each point, and every time it gets distorted the geometry changes, and at every change in geometry you have to find the new behavior of fluid, right? So yeah, that is about FSI, or fluid structure interaction. Now uh, I'm not going to get into details of species transport and combustion modeling and radiation modeling. So these are just different topics in CFD, which I won't be covering, um, and or I'll just may as well cover it later, because it's not required right as of now. So yeah, this is so this was everything about CFD that I could give you. So we are now done with CFD. So I mean, yay. Yeah, we completed CFD. So I don't know how many hours totally it took. Uh, I mean, I'm assuming it's around, I don't know, 4 to 6 hours of lectures. But yeah, if you see this, you can just, I mean, you can say that uh, quite a lot of CFD now. I mean, quite something of CFD now, right? And I've gone in detail of everything. So if you have gone through this, you are very well prepared for interviews and anything related to the background of how CFD works, right? Again, now CFD is a practical, I mean, it's something that you simulate, so you can just experiment all these in ANSYS Fluent or SU2 or your open form. Now, since you know everything that works backend, you can understand each uh, terms in the software. And again, there are like tons of terms and functions in CFD. So if you don't understand any of them, you can just ask any LLM like ChatGPT or Claude to know what, or Gemini to know what that function does, right? So yeah, this was everything about CFD. So if you have any uh, doubts or anything, you can just DM me. So again, you can DM Kashyap, Binu, right? In link at I mean on LinkedIn. And yeah, that should, and I will respond. And there are a lot of names with Kashyap, and I'll just search the one in NITK, that's National Institute of Technology, Karnataka, right? Um, so yeah, that is all about CFD as a whole. I hope you have understood CFD till wherever I've thought. And if any doubts again, just you can reach me out. Or yeah, that's all. So thank you everyone for watching till here. If you have completed the series, well done, yay, congrats, and yeah, bye.